SwayamPrabha. Digital India. Educated India.
After Pelton wheel, I'd like to discuss today on reaction turbine. As I have told, I'll discuss today on reaction turbine. The contents of the lecture are Francis turbine, blade efficiency of a Francis turbine, degree of reaction, net head across a reaction turbine with a draft tube, specific speed and the wheel geometry. And then I'll discuss on Kaplan turbine, blade design, and the free vortex flow concept. I'd like to initiate the discussion with a cut section of a Francis turbine. Please indicate that water is passes through the volute casing and then enters the impeller via guide vane, and then the water is pushed through the reservoir or the sump via the draft tube. Thereby, the volute casing, guide vane, impeller, and the draft tube are the integral part of a Francis turbine. And Francis turbine is a reaction turbine. Thus, I like to indicate here the primary features of a reaction turbine. Those features are the part of the total head available is converted to the velocity head before the entry to the turbine, and the remaining pressure drop occurs in the rotor. Hence, the static pressure of water gradually decreases as it flows through the runner. The flow completely fills all the passages in the runner, unlike to a Pelton wheel. Furthermore, the guide vanes are used to control or direct the flow. Further, a draft tube is normally added to the turbine exit. This draft tube is also considered as an integral part of the turbine. So these are the features of a reaction turbine. I would like to illustrate about the features of a Francis turbine. The Francis turbine is a mixed flow reaction turbine. Moreover, a reaction turbine is usually well suited for low head and high flow rates. I have already indicated earlier, but further I like to add here that the static pressure of fluid gradually changes as it passes through the impeller, varying the cross-sectional flow area of the runner passage. An American engineer, James B. Francis, 1815 to 92, during this year, he developed a radial flow hydraulic turbine of reaction type, which is named after him as Francis turbine. Most of the Francis turbine have vertical shaft cross-sections, although some of smaller machines have horizontal shaft. The schematic of a Francis turbine is indicated in figure 1 in the next slides. Figure 1 illustrates a vertical shaft Francis turbine in different views and figures to illustrate the different features. Suppose here I have given a schematic of the whole system to illustrate that the turbine is connected to the reservoir by a long pipeline which is called penstock. So thus penstocks push the water to the turbine, and then the water is ejected after flowing through the volute casing and the turbine via duct to the lower sump. And thus from this picture one can appreciate what is the head available at the NT to the turbine. Another picture I have indicated here, which is a solute modeling and the cut section presenting the volute casing and the runner of a Francis turbine. One can appreciate here that water enters by volute casing, and the area in the volute casing decreases, and thereby it maintains constant speeds around the speeds of fluids around the impeller. And here the fluid entered the impeller via guide vanes. The position of the guide vanes can be altered also through a servo mechanism. Thus the guide vane control and direct the flow at a proper angle at the entry to the runner, and then water flowing through the runner, it is pushed to the reservoir by a drop tube. Furthermore, I have given here the two sectional view of a Francis turbine, illustrating that the area of the volute casing is gradually being decreased, so that at every section or at every guide vanes, the water enters with almost constant speeds. Furthermore, one can appreciate the impeller here. In another section, one can find the guide vane and the impeller, and here you can see that the direction of the flow within the impeller passage changes from radial to the axial direction. That's why impeller is a mixed flow impeller here, and then it is pushed to the water is pushed to the lower reservoir via the drop tube. Thus, in this figure, the different schematics or the models have been presented to illustrate the overall features and constructions of a Francis turbine. I have presented here for your appreciation the picture of a real Francis turbine. This section is the inlet, and this is the exit of the impeller. And the impeller is of mixed flow type. Thus, a Francis turbine comprises mainly of four components. One, the spiral volute casing. The second, guide vanes. Third, the runner or the impeller, and the fourth is the draft tube. Let me discuss about the spiral casing. I have indicated here in brief about its feature. Fluid enters the spiral casing that surrounds the impeller or the runner. This spiral casing is known as volute or scroll. The flow rate along the fluid path in the volute decreases due to continuous entry of fluid to the runner through the guide vanes. Thus, the cross-sectional area of the volute decreases along the flow path so that the flow velocity remains almost constant. I have discussed now about guide vane. The essential purpose of the guide vane is to convert a part of the pressure energy of fluid to the kinetic energy and then to direct the fluid onto the runner at the most appropriate angles. Moreover, the guide vanes are provided to control the flow rate through the runner. Thus, they can be turned by a suitable governing mechanism regulating the flow rate when the load changes as indicated in figure 2. So in figure 2, I have illustrated the two positions of guide vane. One is done by firm line and other position is done by the dotted line. Please note that for the position which has been illustrated by dotted line, the flow area is much less and thus the flow rate. Hence, the flow rate can be controlled by turning the guide vane by a governing mechanism. Furthermore, guide vane impart a tangential component of velocity and hence an angular momentum to the water before it enters to the runner. Regarding the impeller or a runner about a Francis turbine, I like to state that the angular momentum of water is reduced as it passes through the runner and thereby supplying work to the turbine shaft. A combination of radial and tangential components of flow is observed in the runner of a Francis turbine. Here the flow is inward, that is, it flows from periphery towards the center. Further, please note that here the direction of flow changes as it passes through the runner and finally it becomes axial entering to the draft tube. The shape of the runner depends on its specific speed. Thereby, while designing an impeller, one should assess what is the specific speed. The draft tube, as indicated here, is a conduit that connects the runner exit to the terrace where water is being finally discharged. The primary function of the draft tube is to reduce the velocity of the discharged water at the outlet. Thus, the draft tube acts as a diffuser by ensuring maximum recovery of energy by significantly reducing the exit kinetic energy. Further, it permits the turbine to install above the terrace without any significant drop of available heat. Please note that this is important point, that the draft tube permits the turbine to be installed above the trail water without any significant drop of available head. This I will explain later. The exit of the draft tube must be submerged below the level of water in the threadless so that the turbine remains full of water. After the discussion of different components of a Francis turbine and about their feature, I like to discuss here the benefit of using a draft tube for a reaction turbine and the net head available across a Francis turbine. Let me comment now about net head across a reaction turbine with a draft tube. Figure 3 shows a flow diagram from a reservoir via a reaction turbine to the tail race as indicated here. And this schematic would give us the idea of head across a reaction turbine. What I have illustrated here, I have indicated a penstock which is connected to the turbine, and turbine in turn is connected to the draft tube. Therefore, finally water is being discharged via the draft tube that reduces the kinetic energy of water from the outlet of the turbine. Thus, draft tube is a diffuser. Here I have indicated the features of a draft tube, stating that the effective head across a turbine is the difference between the head at inlet to the machines and the head at its outlet. So all can imagine now the effective head, which would be here the head drop because of flow through the turbine. That is the difference between the head at the state point 1 minus head at the state point 2. However, at the state point 2, what is the kinetic energy of the fluid? That can be treated as a loss. Now, the sum part of this exhaust kinetic energy can be recovered with the draft tube. Again, I like to say that the sum part of this exhaust kinetic energy can be recovered with the draft tube. Thus, the effective head available can be substantially improved because of draft tube than without draft tube. Furthermore, one should note that the draft tube being a diffuser, the angle of divergence be limited to 8 degrees to prevent the flow separation. Thus, while designing a draft tube, the angle of divergence should not cross 8 degrees. Otherwise, its performance may deteriorate because of flow separation. Figure 3 here indicates the same flow diagram, and here one can appreciate that the turbine is installed above the tail race by an amount Z. So Z is the elevation, and the inlet and exit to the turbine is indicated by the point 1 and 2. Thus, the total head at the entry and exit of the turbine can be found out by applying the Bernoulli equation as H1 is equal to P1 by rho g plus C1 squared by 2g plus z, which is the equation number 1. And similarly, H2 is equal to P2 divided by rho g plus C2 squared by 2g plus z. That is, the total head is equal to the pressure head plus velocity head plus z height. Now the overall head can be expressed as H0 equal to H1 plus HF. HF is the loss of head due to friction in the penstock. Please note that I have indicated here H1 and HF. So H1 and HF has been marked here along with C1 squared by 2g, which is the velocity head at entry. Now, the net head available to the runner is given by H1 minus H2, which is equal to H. That's equation number 4. So I have defined here overall head, and also I have defined here the net head available to the runner. Figure 3 indicates that the state point 2 is the exit of the turbine and 3 represents the exit of the duct tube. Now, with the duct tube, one can say H2 is equal to H3 plus H suffix Fd, where small h suffix Fd represents the frictional loss in the duct tube. Now, neglecting friction loss in the duct tube, we have H2 is equal to H3, which is the equation number 5, where H3 is equal to C3 squared divided by 2g, because at the state point 3, the pressure is almost equal to the atmospheric pressure and Z being 0. Thus, H2 is equal to C3 squared divided by 2g. Hence, the net head available to the runner becomes H is equal to H1 minus H2, that is H1 minus C3 squared divided by 2g, which is given by the equation 6. Thus, please note that the available energy to the runner has increased because of addition of duct tube. Thus, I have illustrated here the purpose of providing a duct tube. A duct tube allows the turbine to install above the tail race without any drop of available head. The second point is the more available aid for energy conversion because of reduced exhaust kinetic energy, since now the duct tube can be considered as an integral part of the turbine. The third point, a vacuum pressure that is below the atmospheric pressure is maintained at the exit of the runner now because of addition of duct tube. Thus, there is a chance of cavitation, which will be discussed later. Now, at the exit of the impeller from equation 5, the static pressure can be expressed as P2 divided by rho g plus C2 squared by 2g plus z is equal to C3 squared divided by 2g. Thus, P2 by rho g is equal to minus within the bracket minus z plus C2 squared minus C3 squared divided by 2g. Equation number 7. Hence, The static pressure at the exit of the impeller is below the atmospheric pressure. The minimum local pressure at the outlet should never fall below the vapor pressure of liquid at the operating temperature to avoid the problem of cavitation. This limits the size of the top tube. Now I'll derive the expression for blade efficiency and degree of reaction of a Francis turbine and correlate them with flow angles. The meridional view of a Francis turbine at a mid blade height along the inlet and exit velocity triangle have been presented here. I have illustrated earlier about the meridional streamline or meridional circumferential section. So you may imagine that I have considered a meridional circumferential section passing through the mid plane, and let U1 be the inlet blade speed and W1 be the inlet relative velocity to the rotor, and thus C1 be the absolute velocity at entry. Similarly, W2 be the relative velocity at exit from the blade, and U2 be the blade speed at exit. Thus W2 plus U2 result in C2. Now here C2 in the radial direction. I have projected here the velocity triangle. I have taken a blade which is the meridional section of the blade, and thus I have indicated here U1 plus W1 would be equal to C1, and beta 1 is the relative inlet angle, alpha 1 be the absolute inlet angle. So one can imagine here CM1 and C theta 1. CM1 be the meridional velocity at inlet, and C theta 1 is the swelling component at inlet. Similarly, at exit, W2 is the relative velocity plus U2 would be equal to C2. Now, alpha 2 is 90 degree here. Beta 2 is the relative exit angle, and CM2, that is meridional exit velocity, which is connected to the flow rate, should be equal to C2 here. So this is the velocity triangle related to a Francis turbine runout. Please note the velocity triangle here at inlet. So I have indicated C theta 1, which is swelling component at inlet, and this is W theta 1. Furthermore, at exit, here C theta 2 is equal to 0, and please note that the design is such that CM1 is equal to CM2, that is meridional velocity at inlet and exit, they are made equal. Now from inlet velocity triangle, one can write CM1 divided by C theta 1 is equal to tan alpha 1, and thus C theta 1 is equal to Cm1 into cot alpha 1, which is the equation number 8. Similarly, I can write Cm1 divided by W theta 1 is equal to tan 180 degree minus beta 1. Thus, W theta 1 is equal to Cm1 into cot within bracket 180 degree minus beta 1. Further, the blade of a Francis turbine are always so shaped that the tangential or the swirling component of velocity at exit becomes 0, that is C theta 2 is equal to 0. In that case, C2 or alpha 2 would be equal to 90 degree. This made the kinetic energy exit at a minimum level. Furthermore, the flow velocity remains constant throughout the machine, that is Cm1 is equal to Cm2. With respect to velocity triangle, particularly at the exit, there is an error regarding the direction of W2. So the direction of W2 would be like this. Okay. Now, the energy transfer to the rotor per unit mass flow rate can be obtained from the Euler equation for turbine as small w is equal to U1 into C theta 1. Since C theta 2 is equal to 0 here. Furthermore, U1 can be given by C theta 1 minus W theta 1. If you note that this is C theta 1 and this length indicates W theta 1. So U1 would be equal to C theta 1 minus W theta 1 from inlet velocity triangle. Again, U1 would be equal to, put the value of C theta 1 as W theta 1, then U1 would be Cm1 cot alpha 1 plus Cm1 into cot within the bracket 180 degree minus beta 1. Thus, it would be equal to Cm1 into cot alpha 1 plus cot beta 1. Thus, from equation 10, which is the Euler equation for turbine, W equal to U1 C theta 1, that is equal to Cm1 square into cot alpha 1 within the bracket cot alpha 1 plus cot beta 1. That is equation number 13. Now the kinetic energy at outlet of the impeller can be treated as loss. Thus kinetic energy at the exit is equal to C2 squared by 2, that must be equal to Cm2 squared by 2. Thus please note that exit velocity triangle and C2 would be equal to Cm2, and that's also would be equal to Cm1. Hence, the blade efficiency of a Francis turbine can be expressed as eta B is equal to small w, that is specific work output, divided by small w plus Cm2 squared by 2. That can be expressed as small w divided by small w plus Cm1 squared by 2, since Cm2 equal to Cm1. Now put the value of small w, which I have derived earlier. Thus, blade efficiency can be expressed as twice Cm square cot alpha 1 within the bracket cot alpha 1 plus cot beta 1 divided by Cm1 square plus twice Cm1 square into cot alpha 1 within the bracket cot alpha 1 plus cot beta 1, which can be written as eta b is equal to 1 minus 1 whole divided by 1 plus 2 cot alpha 1 within the bracket cot alpha 1 plus cot beta 1. This is equation number 15. Thus, equation number 15 is an important equation which states the efficiency of a Francis turbine blade, the degree of reaction of a Francis turbine. The change in pressure energy of fluid in the rotor can be evaluated by subtracting the change in its kinetic energy from the total energy released. Now, with respect to velocity triangle, please note that C1 be the inlet absolute velocity to the runner and C2 be the exit absolute velocity. Now, the half into C1 squared minus C2 squared represents the change in kinetic energy as the fluid passes through the impeller. Thereby, R is defined here as W minus half C1 square minus C2 square divided by W, where W represents the total energy released as the fluid passes through the turbine. Now, from inlet velocity triangle, C1 equal to Cm1 divided by sine alpha 1. Now I can say C1 square minus C2 square is equal to Cm1 square within bracket 1 divided by sine square alpha 1 minus 1. Since one should appreciate that C2 is equal to Cm2 and Cm2 equal to Cm1. Thus, I can say C2 is equal to Cm1. Thus, C1 square minus C2 square is represented as Cm1 square into cos square alpha 1. Now, from equation 60, the degree of reaction becomes R is equal to 1 minus half Cm1 square into cot square alpha 1 divided by W. Thus, R equal to 1 minus cot alpha 1 divided by 1 plus twice cot alpha 1 plus cot beta 1. That is equation number 17. Thus, equation number 17 is an important relation which gives the expression for degree of reaction. And please note that the degree of reaction of a rotor of Francis turbine depends on flow angle alpha 1 and beta 1. Please note that the inlet blade angle beta 1 of a Francis turbine varies in the range 45 to 120 degree, and the guide vane alpha 1 from 10 to 40 degree. The ratio of blade width to diameter W by D of a runner of Francis turbine at the inlet depends on the specific speed ns and W by D varies in the range of 1 by 20 to 2 by 3. So from this expression, one can appreciate there is a wide variation of beta 1 and W by D, and this depends on specific speed. Therefore, the specific speed and wheel geometry, they must be correlated, and this correlation I'll express now. So I have written in brief that for a Francis turbine, the variation of geometric parameter like alpha 1, beta 1, W by D depend on the specific speed Ns, where Ns lies in the range 50 to 400, and the specific speed here is expressed as Ns is equal to n root over p h to the power 5 by 4. That is, this is the power specific speed, where n is expressed in RPM, p in kilowatt, and h in meter. If eta h be the hydraulic efficiency of a Francis turbine, while the power delivered is given by P and head available is H, then eta H can be expressed as P divided by rho Qg into H. And thus P can be expressed as eta H into rho Qg into H, equation number 19. Thus putting the value of P in the expression of specific speed, one can show that Ns is equal to, within the bracket, 1 plus twice cot alpha, within the bracket cot alpha plus cot beta whole to the power minus 3 by 4. So this is the expression for specific speed of a Francis turbine in terms of blade angle. So here please note that equation 20 indicates that specific speed of a Francis turbine is function of blade angle. Characteristics of turbine operating at a part load. When a Francis turbine is required to operate at part load, the power output is reduced by tilting the guide vane to restrict the flow rate, while the blade speed is maintained constant. At a part load, the relative velocity at the runner entry has a high incidence, while the absolute velocity has a large component of swirl at the runner exit. Both these conditions lead to high losses. Thereby, at the part load, losses would increase. Figure 5 shows the variation of hydraulic efficiency for different types of turbine, including the Francis turbines, over the entire range of load at constant speed and constant head. Figure 6 indicates the variation of hydraulic efficiency for various types of turbine over a range of loading at a constant speed and constant head. So efficiency versus load has been plotted here, and this indicates that the Francis turbine suffers most compared to other two at part load, while the Pelton wheel gives the best performance, indicating almost a flattened characteristics at part load. In this section, I'll discuss about a Kaplan turbine, which is an axial flow hydral turbine. I'll discuss about its feature, construction, flow characteristics, and the blade design. I'll discuss now about the couple-on turbine. A couple-on turbine is a high specific speed machine which corresponds to a relatively low head and high flow rate. Please note that for a given diameter of the runner, the maximum flow rate is achieved when the flow becomes parallel to the axis of rotations. Thus, for a couple-on turbine, which is of axial flow constructions, gives the maximum possible flow rate for the given diameter. I have indicated here the picture of a real couple-on turbine, where you can appreciate the turbine having fewer blades, and the blades look like a propeller, very well machined, very well finished rather. And the blades are aerofoil constructions. Such a hydraulic turbine was first designed by an Australian engineer, Victor Kaplan, and therefore it is named after him as a Kaplan turbine. A schematic of the machines will be indicated in figure 1. Please note that the function of the guide vane here is same as the Francis turbine. So I have not illustrates here further about the function of the guide vane. Figure 1 illustrates the schematic of a couple-on turbine. This indicates the guide vane, impeller, the drop tube. And here the impeller are aerofoil shaped and highly twisted. Now between the guide vane and the impeller, the fluid in a couple-on turbine turns through a right angle into the axial direction and then passes through the runner. Thus, the fluid enters the impeller axially and leaves axially. Furthermore, please note that the runner usually has 4 to 6 blades and closely resembles a ship's propeller. Thus, it is often referred as a propeller turbine. Neglecting the frictional effect, the flow approaching the runner can be considered as a free vortex. Thus, the wheel velocity is inversely proportional to the radius, while the blade velocity is directly proportional to the radius. Thus, I like to say here that C theta component at inlet would be inversely proportional to 1 by R, and U, blade speed, would be proportional to R. The different relationship of the fluid velocity and the blade velocity with changes in radius would lead to a highly twisted blade for a couple-on turbine. Figure 2 indicates the velocity diagram at the inlet to and exit from the runner of a couple-on turbine at the mean radius, that is R is equal to Rm. Thus, let us consider the mean section, which I have drawn by the reading. Now this is a circumferential section. However, as I indicated earlier, this is the runner of a couple-on turbine. This is actually hub, and the blade are mounted on the hub, and the blades are aerofoil constructions. And the section 1 indicates the inlet to the blade, while section 2 indicates the exit from the blade. Now, the circumferential section, if I cut and stitch on a plane of paper, I'll get the blade profile, which are aerofoil section. This is the blade profile. And the velocity diagram has also illustrated here. So U is the blade speed. Therefore, at inlet, U plus W1 would give C1. W1 be the relative inlet velocity, and C1 is the absolute velocity, where U is the blade speed. Similarly, beta 1 be the inlet relative flow angle, and alpha 1 be the absolute flow angle at inlet. And here both beta 1 and alpha 1 are projected with respect to the peripheral direction, and exit W2 be the relative velocity and C2 be the absolute velocity. Thus W2 plus U would lead to C2. Here C2 would be equal to CZ, that is equal to axial direction or flow axial component of C, that is CZ, and alpha 2 be the absolute angle and beta 2 be the relative flow angle at the exit. Here alpha 2 would be equal to 90 degree. That means C2 will be in the axial direction here. Now, I have already indicated that C theta at inlet is inversely proportional to the radius 1 by r, while blade speed U is proportional to r, considering that if I draw the velocity triangle at different section, we would realize that it lead to the twisted blade. To make you understand what I have taken three sections. One is near to the hub, one is the central line, which is indicated by red, and another I have drawn by blue, which is a section near to the tip. Let me project the blade profile on these three respective sections. If I do that, and if I project on a plane, how they will look at that is the mid-section profile I have already indicated. Let me draw again with a red ink. This is the profile for the mid-section. Let me draw a profile for the hub. This is the profile for the hub. Let me draw a profile for the section which is close to the tip. This is the profile for a section which is close to the tip. Thus, one can appreciate the blade is highly twisted. So I am looking now all the section from here. After this illustration, you have appreciated how the blades are in reality. Thus here I have indicated the blade angle with respect to the tangential direction at a plane near the hub is greater value than that at a tip. Similarly, one can imagine stagger of the blade profile near the root would have a higher value than the tip. Furthermore, the high degree of twist of a couple-on turbine can be related to the strength of circulation around the blade, and that I'll explain you in the next slides. If the flow is assumed to be a free vortex just upstream of the runner, then Rc theta is equal to K, K being a constant. Thus, it leads to C theta is equal to K by R, which is the equation number 1. Again, U is the blade speed is proportional to R, R being the radius, where Cz be the axial component of velocity through the impeller is considered constant for a given design. Now, I have indicated earlier the velocity triangle at the mean section. Now, please note that at the inlet, this is C theta 1, that is component of C1 in the peripheral direction. Thereby, from inlet velocity triangle, one can write cot beta 1 is equal to U minus C theta 1 divided by Cz, and cot alpha 1 is equal to C theta 1 by Cz. Now I can write cot beta 1 is equal to U by Cz minus C theta 1 by Cz, that is equal to U by Cz minus cot alpha 1. Thus, cot beta 1 can also be related to cot alpha 1. Furthermore, putting the distribution of C theta with R, I can say cot beta 1 is equal to omega R divided by Cz minus, putting the value of C theta, I can write K divided by R into Cz. So this equation states that beta 1 is a function of R1. Similarly, cot beta 2 would be equal to omega R by Cz, because from exit velocity triangle it can be stated that cot beta 2 is equal to U by Cz. That beta 2 also became a function of R. Furthermore, cot alpha 1 is nothing but K divided by RCz. So that cot alpha 1 also is a function of R. So this is the relation tell us that beta 1, beta 2 and alpha 1 are the function of R. So the angles, flow angle changes at different radius, resulting in the highly twisted blade. The relations as established earlier, that is cot beta 1 is function of R, similarly cot alpha 1 and cot beta 2, they depict the following variation of flow angle with respect to peripheral direction for a couple-on turbine as presented in figure 3. The figure 3 illustrates the variation of flow angle for a couple-on turbine with radius. So as R increases from hub to tip, beta 1 decreases, alpha 1 slowly increases, and thus beta 2 also slowly decreases with R. Thus, the stagger angle with respect to peripheral directions would vary from hub to tip, while a section near the hub has a higher stagger angle than the tip. Furthermore, the specific work output from the Euler equation for turbine can be stated as a small w is equal to u into c theta 1 as c theta 2 is equal to 0 for the couple-on turbine. The figure here presents the variation of efficiency against the non-dimensional specific speed for different kinds of hydraulic turbines. Here the maximum possible efficiency versus dimensionless specific speed has been presented. Please note that the choice of the turbine depends on the operating condition, that is rotational speed, power, and the head. It indicates that the couple-on turbines operates in the high range of specific speed, while the Francis turbines cover the range between the Pelton wheel and the couple-on turbine, and the Pelton wheel indeed operates in a very narrow band. Furthermore, if I say regarding the governing of a reaction turbine, it's usually controlled by altering the position of guide vanes, and thus the guide vane also is controlled through a servo mechanism as before, or similar to a Francis turbine. Thus, the flow rate is controlled by altering the position of guide vane at the part load. Here I have discussed about reaction turbine, both the Francis and couple-on turbine, about their features, efficiency, apart from constructions. Hope the lecture would be helpful to you. Thank you for listening.